Hi, welcome back again to this course in ABE161. In this video, we'll start our topic on the introduction to reinforced concrete structures. Before we delve into the details of the sizing of the members and then going through the code provisions and the computations, we'll first discuss the overview of these reinforced concrete structures in terms of its, let's say, advantages, disadvantages, and then the properties. Probably not all properties, but the ones that we'll be using or that we'll encounter in the calculations. Okay, so um, reinforced concrete is one of the materials used in building constructions. So we have this selection or choices, let's say building materials. Okay, we have these choices can go for, let's say, reinforced concrete or steel, timber, and other ones like let's say pre-stressed concrete. Okay, so this is different than the reinforced concrete. Okay. Although they both use concretes, but in terms of reinforcement, they're different. So in terms of reinforcement and probably the mechanics, they're different. Okay, so pre-stressed concrete, and then probably the masonry structures. Okay, so in this course, we'll only consider this, the reinforced concrete, steel, and timber. But for now, we are going to discuss the reinforced concrete. Okay, so it's used in building foundations. You can actually find this even in steel structures, let's say portal frames. Um, Even though the structure is steel, the foundation is built using reinforced concrete. Okay, so why is that? Okay, so you'll notice the characteristic of reinforced concrete is that its resistance to the environmental, let's say, environmental degradations, uh, compared to steel. So steel, it corrodes, and timber, um, probably even in the presence of moistures and they say flammability. So timbers they have also um, disadvantages. So reinforced concrete, um, they they offer resistance to that. Let's say moisture and even corrosions. So and also in terms of fire resistance, so uh, they have advantages with respect to those situations. Okay, so if we can list down the advantages, so one is it can be molded to any shape. Molded to any shape. So meaning, like you can, since the construction of this is it's actually mixed and then it's in a wet condition. So it's just molded. So you just design your forms to whatever shapes and then you pour that concrete mix and then you let it dry. And then when it's hard, then you can remove the form. So you get the shape that you like. Okay, so this is very versatile in terms of shape. Okay, any not shape, sorry. Okay, shape. Okay, and then the next is the materials required for concrete are locally available and relatively inexpensive. So just write relatively inexpensive. So recall that um, the materials are just simply sand, cement, um, sand and gravel. Okay, and then fire and water resistance. Water. Okay, so it is fire resistant compared to um, timber structures. At elevated temperatures, of course, it can combust because it is a combustible materials. For steel structures, at elevated temperatures, it has a reduced capacity. So instead of, let's say, having a strength of 250 megapascal, it reduced to, let's say, half of it. So there is a downside. or an evident downside for steel and timber structures um, when it comes to fire and also water. So all the water, it says here water resistance, that somehow um, yes, or somehow, I mean, in a way you can say yes, it is water resistance compared to steel structures, because uh, timber, they they actually warp in the presence of moisture, so they deform, something like that. For steel, they corrode. So without paintings, without protections, surface protections, then they are prone to corrosions. Whereas concrete is not. However, um, concrete is actually a permeable material. So not all concretes are really that tight. So at some degree, there is some permeability. So we have also to. That's the reason why additives are added. Okay, and what else? We have a good rigidity. It's pretty rigid when uh, it solidifies. Um, okay, good rigidity, and what else? And compressive strength. Or let's say compressive strength. Okay, in terms of labor, uh, low grade, or that's low grade. Okay, or not much high skilled labor is required. Labor is required. Okay, so in spite of these advantages, there are also disadvantages. Okay, so that's common in every building materials. So we have advantages, but we also have disadvantages. Okay, so it requires form. So of course, you need form so that you can mold your shape. But that um, but that requirement, of course, is there's an additional material, additional labor. So probably that's the downside in terms of the time. Uh, okay, requires formworks. Relatively low strength. Okay, low tensile strength. So it's good in compressive, but the strength is the tensile strength is not. Okay, and it also undergoes shrinkage. Okay, so there are still, probably there's still other reasons, but so far, at least I guess you already have a um, good understanding on this concrete um, material. Okay, so now let's move on to the details of this concrete as a structural material. So we say that concrete is a material that is strong in compression but weak in tension. So meaning, so for example, this is our concrete material, and I'm trying to apply a load. So if it's in compression, it's good, but if it's in tension, that's bad. Okay, so tensile strength. The tensile strength is 10%, around 10%, so 8 to 12%, depending upon the literatures. But I guess just say roughly that's 10% of its compressive strength. Okay, so that's the problem of concrete alone. So take note, we're just talking about concrete. This is not yet reinforced concrete, but we're building the foundation. Why do we need to reinforce? Why do we need to provide reinforcement in the concrete? So, concrete itself, without reinforcement, is strong compression but weak in tension. So, any loadings that's in compression is okay, but if there are presence of tension loads or tensile stresses, then that's gonna be there's gonna be a problem. Okay, so what's the problem with this, I mean, in terms of the structural applications. So for columns, yes, that's good. But for beams, for flexural members, so recall that in a flexural member, when you are trying to apply a load, say a flexural load, so stresses, okay, these external loads induces stresses inside the materials. Okay, so if we cut this section, okay, so let's say we cut the section, what we get is something like this. Of course, we get a bending and deflection, and also the stresses. Okay, so let's use this color. Or we can just use this. Okay, we can illustrate it this way. So we have a separation, I mean, something like a region wherein the top part is in compression, whereas the bottom part is in tension. So what's the problem with that? Okay, so for we say that concrete is good in compression but weak in tension. So meaning that for flexural members uh, in regions under tension. Okay, so we have this, say, tension or tensile stresses, and then this one is compressive stresses. Okay, so in regions where tension zone exists, then that's going to be a problem because it will crack and then it will just fail. Um, so the point here is we need something to reinforce this concrete material in the tension zone. So that is why we 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 put rebar, right? So we include rebars here at the tension zone. So if you draw the cross section of the beam, then there's gonna be rebars here, right? So this is the main reinforcement. We put it in the tension zone. So take note that tension zone is not always at the bottom. So that depends upon the loading conditions and the boundary conditions. Like for example, for a simply supported beam, our moment, let's say, our moment diagram is like this. So that's a positive moment diagram. But for cantilever, let's say cantilever beam, so we have a fixed boundary condition here, and then apply loads, for example, then you're gonna have a moment like this, right? Okay, but for fixed boundary conditions for a beam under uniformly distributed loads, what you get is actually there is a negative moment and then there's going to be a positive moment, right? So meaning we need to figure out this tension zone. So we need to provide reinforcement at that zone. Okay, so that's one reason why we need to put the reinforcement, is that the reinforcing steel, they're the ones to carry the tensile stresses. Okay, so furthermore, there's also reason there are situations where reinforcement bars are added in the compression zone. So for example, in a column, so we say that concrete is already strong in compression, but with the addition of let's say rebars, so this addition of rebars here, okay, so let's just write addition of rebars provides extra strength to the section, to the member, let's say. Okay, and there are still others, like for example in beams. So in beams, there's also shear in beams. So recall that for beams we have shear and moments. Okay, so we have shear and moments. Now, with regard to shear, then we also provide reinforcement, shear reinforcement in the in the concrete. Okay, so the ones here we already um, introduced. Uh, I already introduced that this to you. So these are the flexural reinforcements, but there's also another type of reinforcement that's present in the beam. So this is called the beam stirrups. Okay, so the method of reinforcing the concrete with steel bars is what we call reinforced, okay, concrete. Okay, so now let's talk about the concrete ingredients. Okay, so I'll just run through this quickly because it's already in our lecture handouts. Concrete ingredients. Okay, so concrete is a mixture of cement, what else? Aggregates, and water. Okay, with or without admixtures. Okay, so 1, 2, 3, 4. Okay, so the cement could be Portland cement, then hydraulic cement. Okay, and for the aggregates, we have fine aggregates, or let's say sand, and then another one is gravel. Coarse aggregates, and that's gravel. The water, and with or without admixtures. Okay, so once that these three ingredients mixes, then after some time it hardens and then becomes a strong material that's is good, or that is suitable for construction or as construction materials. So for cement, we have Portland cement and hydraulic cement. So for Portland cement, there are still other types, like for example type 1, type 2, type until type 5. So general purpose cements, that's type 1, and then other types of cements are uh, are also available, because for example the type 4, or let's say the type 3 develops high early approximately 190% more of the strength as compared to type 1. So high early strength Portland cements are probably uh, so generally you can uh, have early removal of the forms or shortening of setting time. Okay, and there are still many others. For water, so any potable water will do. So just refrain from the use of, let's say, the use of, let's say, salt water, because salt can corrode the steel materials, the reinforcing bars. Okay, then for the aggregates, we have fine and coarse aggregates. So for sand, that's actually less than 5 mm. So this actually depends upon, I think, the the differentiating criteria depends upon the standard organizations that's being followed. Okay, so for us here, we'll just use, okay, less than 5 mm, that's sand, and then if it's um, greater than 5 and between 10 mm to 40 mm, then that's gonna be gravels. So I'd like to highlight these coarse aggregates because there are this term, like for example crushed stone or crushed aggregates. So these are aggregates that are actually having this kind of shapes. Okay, so with a lot of sharp edges, because they're actually crushed in a machine, so that's why they're called crushed stone or crushed aggregates. So instead of having a smooth, rounded, something like rounded gravels, okay, so that way they increases the surface area, something like that. Okay, so that's also available crushed stones. Now larger than 40 mm, probably you can call it like um, uh, maybe boulders. Okay, so you can there there are terms like something like the boulders, so larger than this gravel size, and there are some more terminologies above this 40 mm. Okay, so for the admixtures, the role of this admixture is to actually alter the properties. So there are admixtures that um, makes makes the concrete mix, let's say, better water tightness, for example, or for example retarders. So instead of having this amount of setting time, it delays the time, or sometimes some admixtures or accelerators or something like that. Okay, so you can read these, the details of this, you can read this in our lecture handouts. Okay, next we'll go to the proportioning and mixing of concrete. Okay, proportioning and mixing of concrete. Okay, so since concrete is a mixture of several materials, then that's gonna affect, I mean, the proportioning of these materials is gonna affect the properties of the concrete. Okay, so number one, let's discuss about the water cement ratio. Okay, so water is necessary for the reaction to take place in the concrete mix. Okay, that's given. We need water so that it can have the reactions, but it greatly affects the strength of concrete. So if there is a graph, a water cement ratio graph, we have a water cement ratio on the horizontal axis, and the vertical axis we have a compressive strength, right? So compressive strength. Okay, so there is a graph something like this. So the higher the water ratio, you see that, okay, this is going to the right, means the water ratio is higher, and then going upward, meaning compressive strength is high. So you see that the higher the water, the more water you put, the less strength you get. Okay, so that's it, high water. But if you get low water, then you get a higher strength. Okay, so of course, there's gonna be some amount of something like an amount of water that a reaction can take place. Okay, so the problem is this: since, for example, you are trying to, there's a form. Let's say form works, and then you have braces, for examples. Alright, so let's say include brace. Okay, so you need to pour the concrete here, for example. Okay, so the problem is, okay, fresh concrete. Okay, so the problem is if there's too much, if there's less water, if there's not much water, then probably you wouldn't be able to pour the fresh concrete into the forms. So that affects the that affects the concrete sections, for example. Okay, so there might be some parts that are voids because the concrete wasn't able to flow well. Okay, so that's going to be the problem for less water. And for high water, okay, that's fine. Okay, you can pour it out. You can have, I mean, the fresh concrete can flow through the forms better, but you get a reduced strength. So the question is, how much amount of water is necessary in a given mix? Okay, so the question is, how much water? Okay, so that can be determined by the use of a slump test. So basically, the slump test is to determine the consistency. Okay, when we say consistency, it means the degree of wetness. Whereas another one is workability, it refers to the ease of. Okay, there's another term. We can just write it here. Workability. Um, this one refers to the ease of placing. Okay, ease of placing the concrete mix in forms without segregation. So take note of the word without segregation.